Thank you very much for this opening. I'm very happy to introduce the first keynote speaker, that is Idit Keidar. She is professor at VRF Faculty of Electronical and Computer Engineering at Technion. And she has served as a program chair for number leading conference in our community. Her main research interest is the theoretical foundation of distributed or concurrent system. In order to help, meaning to explain or to improve the implementation that can be done and on such system. And I will say that a very good example of that approach is the topic of the today's keynotes on some of her work on Byzantine Agreement. So I'd like you.
Thank you, Colette. You should share my screen now, I guess. Okay. Just a minute. How do I also share the? Do you see my screen now or not?
Yes.
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 How do I share also my audio?
We can hear you, that's so fine.
No, the computer audio. Sorry.
Can you play something? See if we can hear it.
Yeah, no, I know I need to. Yeah, no, here, share sound. Okay. Okay, got it. Sorry for that. Okay, so you see my screen?
Yes.
Yes, great. So let me start off by thanking my wonderful, my wonderful co-authors. This talk is based on two papers. The first one is with Shir Cohen and Sasha Spiegelman. It was at this last year. And the second one is from Poitiers this year with Oded Naor and Lefteris Kokoris Fogias, and the same as Sasha Spiegelman, and you see their pictures here. So let me tell you what this is about. We're talking about Byzantine Agreement. But by the way, if people can turn on the cameras and ask me questions while I'm talking, I feel like I'm talking to a so a gallery of pictures. Okay, thank you. So the problem we're trying to solve is Byzantine Agreement, as probably most of you know. It's the problem of reaching agreement or consensus among end processes, and the processes can fail by behaving in an arbitrary way. We call this a Byzantine fault. They don't have to follow any protocol. They can do whatever they want. And so if we can tolerate these types of systems, we have an algorithm that is very robust. And specifically, I'm going to talk about not only one agreement, which is Byzantine Agreement or consensus, but also a series of agreements that we can do in order to implement state machine replication or a shared ledger, financial system, or something like that. And that's basically a service that allows processes to broadcast messages so that the broadcast is reliable in the sense that all the messages from correct processes are received, and processes receive the same messages, and also in the same order. That's an atomic broadcast service. So as you might have heard, there are quite a few new frontiers for this type of service, even though it's kind of, the foundations have been studied for a while now. It's become popular because people use it for blockchains, for financial companies, and they put some logos here, but there are, of course, many more. And, question to ask, because, okay, fine, so there are these new applications, all these blockchains, we didn't have them before. But Byzantine Agreement is a foundational problem. The research about the foundations of this problem have been around for 4 decades, right? It was introduced in 1980, and the number of citations for these 1980 papers shows you that it has been widely studied since then. So why are we talking about it now? Again, what else is there to do after all these 4 decades of research and thousands of papers? And I will argue that the main use case for Byzantine Agreement until this blockchain era only considered a handful of processes. Normally, you would see examples with 4 processes at the most. You'd see 7, and you would, or 9. I don't think I saw papers that use bigger test beds or that considered the problem to be relevant or practical in larger systems. And now we're talking about very, very large scale systems with hundreds of nodes, and so the considerations are different. And this kind of reminds me of the role of a CTO in some companies. You know, the role of a CTO is they come to an engineering meeting and the engineers talk and talk and talk, and then the CTO says, but will it scale? Okay, so yeah, that's kind of the next question. Okay, so we have all these protocols, but will they scale? And when we talk about scale, we talk about 2 things. The first one is the message complexity, and here is maybe you've seen this. There's a blog by James Mickens where he was making fun of all the Byzantine Agreement papers before the blockchain era became popular. So that's why you have 4 servers. That's the typical use case for Byzantine Agreement then. And he shows the protocol, and basically you can see that the protocol sends a lot of messages. So yeah. The protocols do send a lot of messages, and really the first issue for scalability is the communication complexity. How many messages do we need to send? And we count the communication complexity by combining the combined complexity of all the processes send together. And again, if we go back to the 80s, there's a lower bound by Dolev and Reischuk from 1985 that says that you need at least a quadratic word complexity for Byzantine Agreement, even in synchronous settings. But this lower bound is deterministic. So the protocols that we've talked about, or from the previous era, they had high complexity. It wasn't as much as a big deal because n was not big enough for it to be painful, for n squared to be painful. And that they did the best they could because most of them were deterministic, and you can't do better in deterministic algorithms. So now what we're going to do is we're going to circumvent these lower bounds, but we're going to use randomization for that. And the second aspect of scalability that is actually very important is the scalability in the scale of the system, in the heterogeneity of the system. When you have a small replication cluster in a single data center, maybe you can say the communication is synchronous because the nodes are probably tightly coupled and messages arrive quickly and you can detect failures fairly accurately. But when you start look at Bitcoin, for example, spread machines all over the world and in different domains, and sometimes they're up, sometimes they're down, sometimes there are network problems. The system, if you want to model it as synchronous, which is what Bitcoin does, then your timeouts have to be in the order of minutes. And indeed, in Bitcoin, you need to wait 10 minutes for a transaction to be approved, which is not a reasonable waiting time if you actually want to, buy something at a vending machine. That's the example it's always given. So, so again, if we want to be scalable, if we want to be robust in large scale, then we must move on away from synchrony and into asynchrony. So we do not depend on communication latency bounds for correctness. And as probably most of you know, That also means that we need a randomized solution due to FLP. We cannot find a deterministic solution for consensus or for Byzantine agreement in an asynchronous setting. So these are the two goals we're going to try to address: reduce the word complexity to be less than quadratic and allow asynchrony. And both of these are going to be addressed using randomization. So I'm going to present two results towards this end. In the scope of this talk, I didn't have time to talk about more, but should point out that we have a short survey in SIGAC News last year, no, not last year, in February or March, that discusses also other results. But now in this talk today, I'm going to talk about two results. The first one, we're going to use verifiable random functions as our building block. And we're going to solve Byzantine agreement with probabilistic safety and liveness guarantees, and with complexity that is order of n times log squared of n. So it's order tilde of n if we ignore log factors. And this result shows that you can have an asynchronous protocol that is actually sub-quadratic. It's the first such protocol, but it's not very practical for a number of reasons that I will outline. And then I'm going to introduce a much more practical approach. It's going to use a perfect coin or VRFs and threshold signatures in order to produce it. And it's going to solve the repeated Byzantine agreement problem, not just the one-shot consensus, with deterministic safety mounts. And liveness is probabilistic. This is, of course, inherent due to FLP. We can't have both of them deterministic, so we only have probabilistic liveness, but the safety is guaranteed. And this protocol, instead of focusing on the complexity for a single decision, which is the focus of a consensus algorithm, because it deals with Byzantine atomic broadcast and repeated agreements, is going to focus on amortized complexity. And that's the metric we're going to optimize there. Look, not the ideal protocol for one decision, but if you have a large number of decisions, you can get good amortized complexity. So practical. Okay. So I'm going to start with the first one. Any questions about sort of the setting, the model, anything else? No. So this is the first result. It's by my PhD student Shir Cohen from the Technion, and with Sasha Spiegelman from Novi. It's called Not a Coincidence, and it's from DISC 2020. This is the first sub-quadratic asynchronous Byzantine protocol, Byzantine agreement protocol. It has O tilde of n word complexity for the communication and constant latency. Both the safety and the liveness hold with high probability, and it's only for binary Byzantine agreement, not multi-valued. I just want to point out that this is not the first sub-quadratic Byzantine agreement protocol. There are earlier works to circumvent the Reischuk and Dolev and Reischuk lower bound with randomization, but they made synchrony assumptions. And this is true for the seminal paper of King and Saya from 2011, and also for Algorand, which is we're going to use some ideas from Algorand, but Algorand used them in synchronous settings and later in partially synchronous or eventually synchronous settings, but not in asynchronous settings. So the model, I think, just to put us on the same page, it's asynchronous. We have n processes. It's a permission model. And at most F Byzantine failures, this result does not achieve optimal resilience, and it has to be roughly 4.5 times F, and that depends on all kinds of parameters of the system. The exact number, but roughly that's what you get for certain parameters. And the cryptographic tool we assume is a trusted public key infrastructure. And in fact, it has been shown in a number of works that this is inherently required for any protocol that's going to be sub-quadratic, even if it's synchronous, not only if it's asynchronous. The adversary model is kind of a middle ground between an oblivious adversary and an adversary that sees everything. The adversary is adaptive, can see the communication, but it takes it time to respond to it. Specifically, when the messages are transmitted, the adversary can't use messages that are currently sort of in the air, in the network, in order to decide in which order to schedule them. But once they're delivered, the next message's scheduling can depend on them. So in a sense, this models a practical setting where the adversary can sort of listen to messages and then affect the next messages that will be sent after it listened to the earlier messages, but not the concurrent ones. So that's the formal definition of this adversary. And the cryptographic tool is verifiable random functions. For those of you who don't know what that is, it's basically a pseudo-random function that also comes with a proof that it has been computed correctly. So for example, if we have an input X to the system that the processes know, every process can use its local VRS with its own secret key to produce a random value, VRF-sk of X, and all other processes that know the sender's secret public key can verify that indeed this is the correct function value on X produced by that user. So basically, you can put your hand into this fishbowl and grab a random number, and it comes with the proof that indeed you grabbed it out of the fishbowl and you didn't cook it up. And so processes cannot lie about the values that they've created, but they're unpredictable, at least to a computationally bounded adversary. We're going to use this VRF hammer for two nails, to solve two problems in the system. The first thing we're going to use the VRF for is in order to flip a shared coin. And this coin is not going to be a perfect coin. And first I'm going to show just how to use the VRF to flip the coin. So I'm going to have present a protocol with quadratic message complexity. And then after that, I'm going to use a trick from Algorand of committee sampling in order to reduce the coin complexity to n log. Let's start with just understanding how we can use the VRF in order to flip a coin. So what we're going to do is we're going to generate a coin with success rate rho. That means that for every bit in 0 and 1, there's a probability of at least rho for all the processes to agree on that bit. So if rho is less than a half, there's some probability that they disagree. Okay, so the coin is not perfect, but there is a fixed positive probability for everybody to flip 1 and for everybody to flip 0, and this is what we need for the protocol. So what we're trying to do here basically is to take all these stick-it notes or these slips that we got out of the fishbowl with the random numbers and the proofs, so that these are like the random numbers generated by the different processes, and they all come with their proofs. And we want to use them in order to agree on one, or agree with probability rho on one random number that is shared by all processes. So let me show you how this can be done in a synchronous setting, synchronous, not asynchronous. As this is a sort of a short note by Mikali from 2017. Basically, all the processes draw their random values from the fishbowl. They have these little sticky notes, and now they broadcast them to one another. And after one round of broadcast, every process returns the least significant bit of the minimum value that it received. Now, because the system is synchronous, we know that all the correct processes receive the messages of all the correct processes. And as for the Byzantine processes, some correct processes may receive their messages while others don't. So if the VRF, the minimum value belongs to one of the Byzantine processes, it can cause the correct processes to disagree, because some of them will receive its message and some of them won't. But whenever the minimum VRF value is by a correct process, we win, right? All the correct processes receive this value and we win. They all select the same bit. So we have a success probability of at least 2/3 if we have the optimal resilience of 1/3 Byzantine. Great, but this requires synchrony. What's the challenge in using this for an asynchronous setting? The challenge is that in a synchronous setting, we can't just say we run around and then all the correct processes receive correct processes messages. We need a different condition to wait for, because we don't know how long messages take to arrive. So the standard way to design asynchronous protocols is to wait for n-f messages, because we know there are at most f faulty processes. So every node is guaranteed to receive n-f messages. So now, when we wait for n-f messages, we're in a different situation, because f of the n-f messages that a process does receive might be from faulty processes, and then another f correct processes messages are missing. We don't know. We have some uncertainty here, and different correct processes might receive different messages. Well, it turns out that this is fixable with another round of communication. If all the nodes wait for n-f messages and then send the minimum value they've seen, and then again wait for n-f messages, then this can be analyzed to show that indeed there's a certain fixed probability for all of them to flip the same coin. And this analysis uses the idea, the principle of common values. We say that a value is common if it reaches f+1 correct processes in the first round. And we observe that every common value is seen by all correct processes in the second round. Okay, once we have f+1 correct processes sending it in the second round, then we know that all the correct processes receive it, because each correct process misses at most f messages from correct processes. And what we prove, and I won't show this proof now, but it's very technical, but it's kind of messy, but it works, is that we can give some lower bound on the number of common values, and that's going to give us a positive probability for actually constant probability for the global minimum to be common, and that's what we need. So we have a constant success probability. Okay, so a little messy math, but that's what it comes down to. Okay, great. So now we have a protocol, but the complexity is still n squared, right? And our goal is to try to reduce this complexity. So now we're going to use our VRF hammer for second nail, for second problem, and we're going to reduce this n squared message complexity using the trick called cryptographic sortition that was introduced in Algorand, that basically reduces the complexity from n squared to n log n. And the idea of cryptographic sortition, or VRF-based committee sampling that's used in Algorand, is to use the VRF in order to sample a committee of order log n processes in each round. The constant here come out of some analysis, and they define the error probability, but let's just say order log n. And now we're going to reduce the all to all rounds with committee to all rounds. So we're going to have log n processes sending messages, but they're going to broadcast them to everybody. The idea is that we're going to use a new committee in each round, so our delayed adaptive adversary can't block or take over the nodes that already sent their messages. It can only take over them for the next round, but in the next round, there's going to be a different committee. so that it doesn't help the adversary. So the adversary can't fool us. Because we can't guess the next committee, we have to send it to everyone. So that's why we have the committee to all pattern. And then using turn-off bounds, you prove that not too many faulty processes in each committee and everything is fine. So here's the idea. The nodes that are highlighted in purple are the ones that are selected for the committees in each round. So in the first round, we have some correct processes and some Byzantine processes, and only they send messages. And if some Byzantine process that was not selected for the committee would send a message, this message would be rejected and ignored because it can't use the VRF to prove that it was selected for the committee. The VRF is verifiable. We can make sure that it's not in the committee. And then in the second round, we have a different committee and only they transmit messages. So awesome, right? We got word complexity and log n because we have log n processes sending n messages each, and we're happy, right? But what's the problem? Does anyone see a problem here? What's the snag? Any guesses? So, okay, so we have this protocol, right? And we send the message. And before we did this, we waited for n-f messages here, right? And we waited for n-f messages in the second round again. Okay, now, yeah, we got n log n messages, but how many messages do we wait for? We can't wait for n-f messages because we're using random committees. The size of the committee is a random variable. The number of correct processes in the committee is a random variable. The number of Byzantine processes in the committee is a random variable, right? So we can't just wait for n-f messages. So one of the main technical difficulties that we address here is to replace the n-f and the f+1 with parameters w and b. So w stands for wait. It's the number of processes to wait for, and that's what we wait for instead of n-f. And b is the number of bad guys or Byzantine guys, and that's replacing f. And we choose w and b so that we can prove with turn-off bounds that with high probability, at least w processes in each committee are correct. At most b processes in each committee are Byzantine. And moreover, we get the intersection properties that the protocol needs. So if we have two processes that both wait for w messages instead of n-f, we knew that if two processes waited for n-f messages, they would intersect in at least one correct process. Well, we want the same property here. Okay, so b+1 is at least one correct process, and they wait for w messages. And similarly, we need an intersection between committees of b+1 and of w. So we have these conditions, and we choose the parameters so as to satisfy them with high probability. They all come into play as constants, but the committees are still logarithmic. So now finally we get the protocol. I'm calling it Shir Cohen's shared coin because it's by Shir Cohen, my PhD student, and this is the protocol. I'm just gonna briefly touch on the fact that once we have a shared coin, we can implement a Byzantine agreement with high probability using a building block that we call a prover. I'm not gonna get into the details of this protocol. I'm just gonna show you one little trick that we use there. Basically, the algorithm is based on Reliably Broadcast, and it's been used for Byzantine agreement before, for example, in the paper by Mustafawi now. But what we do is we convert it to work with committee sampling. And I'm gonna skip the specification of this building block. It doesn't matter for now, but I'm just gonna point out a little trick that we have to do is that if you look at broadcast and protocols in this mode, they have a phase, an echo phase, or boosting phase, where if processes receive f+1 copies of a value, they broadcast it. So we make sure that everything that is seen by f+1 processes is seen by more. And the problem with this phase is that in the echo phase, processes might echo multiple values. So if we use a separate committee for each round, we would still have to have the committee of the second round speak twice. So here we actually take advantage of the fact that it is only binary Byzantine agreement, and we just select two different committees, the purple one and the green one for zeros and for ones, and then a separate committee echoes the zeros and the separate one echoes the ones, so we don't have processes speaking twice, so we can still win against the adversary. Okay. This algorithm actually sends chains of signatures from all the messages it received. So the complexity, the original complexity is n cubed, but here with the committee sampling is n log squared of n. And then we put it together and we get a consensus algorithm. The consensus algorithm is basically just calling these building blocks, the approver and the coin. It doesn't involve any additional communication, so it doesn't change the communication complexity. And the complexity we get is order n log squared of n. So to summarize, we got randomly sampling committees using cryptography in an asynchronous setting. We get a sub-quadratic Byzantine agreement, constant latency, or tilde complexity. But this protocol also has some shortcomings, and they are that it solves only binary consensus. Its safety and liveness both hold with high probability only, and it's a one-shot algorithm, and it actually cannot be used repeatedly for multiple consensus instances, because then the correctness would no longer be with high probability, right? So that's part of the problem of the way we set up the probability. And the resilience is not optimal, but this was actually improved shortly thereafter by Blumenau. But now I'm going to show a completely different approach that's going to tackle all four of these limitations. And I think before I do that, I'm happy to take questions about the first part.
Hi. I do have a question about the adversary model.
Yes.
You mentioned it's I don't remember the name you used, but basically
Adaptive. Delayed adaptive.
Yeah, right. And so what is the impact of this? First, it's actually two questions. Is this the adversary that controls the asynchrony? And so does that mean that messages can be asynchronous only in specific ways? And what would go wrong if we were using a more general asynchronous model?
Yeah, great question. Great question. So the adversary controls the timing, exactly, the asynchrony. It decides basically if you're waiting for W messages, it decides which W messages you're going to receive first, and then you'll move on to the next round.
Mm-hmm.
And if I allow the adversary to, so in the committee sampling, in the coin flipping algorithm, they all send their VRFs. The adversary can see the messages. It can read the VRF values. If it would be able to control the timing now, it would take the minimum value and make sure that some processes receive it and others don't.
Yeah,
we actually rely on the fact that the adversary doesn't use the minimum value in these messages to schedule these messages, doesn't know them yet when it schedules these messages. But in the next round, it can use it. Now, in the next round, it's allowed to use it. Only in this round, it's not allowed to use it.
Okay.
That's a good question.
Yeah, thank you.
Any more questions?
Nope. I have questions. I'm wondering, a correct process could send a message that is received very long time after that. It will not disturb your algorithm.
Yeah, this is also a good point. It's something I didn't mention, but we actually have the round numbers in the messages, so you don't mix them. But I didn't mention this, but right, you if you do multiple rounds, you tell them apart. Yes, good point. Okay, so let's move on to our second algorithm.
DAG,
stop that. But now I'm going to tell you that all you need is DAG. So this is the second work. Model is the same. It's asynchronous with Byzantine fault. Here we do have optimal resilience. So F is any number up to a third. And our cryptographic assumption is that we have, again, a PKI and we have threshold signatures. And we know that if you have a PKI and threshold signatures, you can implement a perfect coin using secret sharing. And there's also sort of a nice aspect to that, that the coin is always safe. So the agreement on the coin is always guaranteed, even in the post-quantum in an era or in stationally unbounded adversary can still not violate the safety because secret sharing is always ensures agreement, but it might hurt liveness because for liveness we need the coin flips to be unpredictable. Okay, so the unpredictability, yes, that depends on computationally bounded adversary. So here we're going to build Byzantine atomic broadcast. And Byzantine atomic broadcast is basically the servers that you use to replicate a state machine where nodes, processes, servers, whatever you want to call them, can propose transactions by broadcasting messages. And then the service delivers these messages to all the processes in the same order. And then they can apply them to the state machine, or if you like the shared ledger view, then the same thing. They can write them on the ledger and they'll all agree in the order in the ledger. So that's the service we propose. And the service, basically Byzantine atomic broadcast is a combination of reliable broadcast, which is something for which many implementations are known, and in addition to total order, which is the consensus aspect of it, because reliable broadcast can be solved in an asynchronous setting with where consensus cannot be. So reliable broadcast basically says that if a correct process sends a message, all the correct processes receive it. That's nice because it gives us fairness. It means that all the nodes get to propose their transactions. Not all blockchain protocols have this property. This property is really nice. And in addition, it says that all the processes agree on the messages, and both of these are liveness properties, and they both hold with probability 1. Okay. To build our service, we're going to use 2 building blocks from the literature that are well established. The first one is reliable broadcast. The most famous algorithm for Byzantine settings is Bracha broadcast. Its complexity is n cubed. There are newer protocols that are randomized. For example, the gossip-based solution of Garawi et al. Has success probability 1 minus epsilon as opposed to probability 1, but is more efficient. And there's also a recent work by Kishin and Tesaro that does verifiable dispersal, which is even more efficient. And we could use any of these, plug in any of these into our protocol. And the second building block we're going to use is unpredictable leader election that is based on a perfect coin. So once we can flip a shared coin, we can choose a leader and then agree on it. And again, because we're using this secret sharing based coin, its information is theoretically safe and unpredictable, which is needed for liveness only with a bounded adversary. So what do? We build a protocol called DAG-Rider in 3 steps. 1, build the DAG. 2, elect random leaders. 3, order the messages. Okay, easy. First step, build the DAG. The DAG represents the causal dependencies among the messages sent in the system. It's a little bit like a blockchain where each block, or block DAG, where each block can point to blocks that precede it. It reflects the communication dependencies, the causal dependencies among communication messages in the system. The DAG is reliably broadcast using one of the protocols I mentioned before. And it consists of about 30 lines of pseudocode. It's very, very easy. What does the DAG look like? We're going to draw in each row the messages sent by each process. So, for example, we have processes sending messages. So the first column of the DAG is going to consist, which is round 0, is going to consist of messages of these, in this example, 4 processes. Next, a process sends its next message in the protocol once it has n-f messages from the previous round. And then it creates these links, these edges to the vertices of the messages that it received in the previous round. So for example, if process 1 received these 3 orange messages, it will create a message that references these 3. And if P2 received these purple messages, it will create a message that references these, and so on. That's how we built the DAG, the communication DAG. So here's an example, a DAG with rounds 1, 2, 0, 1, 2, 3. And each one of these vertices holds the source, sender, and the round number, a set of proposed values, transactions that we want to agree on, and the n-f edges that are pointers to messages from the previous round that it received. These are called strong edges. And in addition, if there are nodes in the DAG that it doesn't have strong path of strong edges to, in this case, it's only this node on the bottom, on the round 2 node, then it creates a new type of edge, which is called a weak edge. Okay, what we're trying to do is we're trying to make sure that this node sees this vertex sort of refers to everything that the node received, even if it received it too late in order to reference it in the next message. So basically, the reason there's a weak edge here is that this message arrived to P1 after P1 sent its round 3 message. So it didn't reference it with a strong edge, but it's just going to add a weak edge to it. And it doesn't add weak edges to things that it has paths, strong paths to, only the ones that are missing. Why do we add the weak edges? We add them for fairness, because we want to make sure that all the messages proposed get ordered. So we use the weak edges for that. This DAG is reliably broadcast. Every node in the DAG is reliably broadcast using one of the protocols I mentioned. So there's no equivocation. All the processes see the same DAG eventually, even if they're temporarily see different subsets of it. Because each node, each vertex contains a linear number of edges, in order to amortize the complexity, we're also going to add at least n messages to each vertex. And so we're going to have, for the cost of setting a linear size message, we're going to agree on a linear size number of values. So the exact reliable broadcast cost depends on the protocol, but we're going to send at least n messages in each of these vertices. Okay, great. That's the first step. The second step is immediate. We need to elect random leaders. The leaders are vertices in the DAG. We're going to take the DAG and divide it into groups of 4 rounds, which we call waves. Hence the name DAG-Rider. And we use the messages in the last round of the wave in order to elect the leader in the first round. So we treat the round 4 messages as shares for the threshold signature, or we use them as parts of them as shares for this threshold signature to produce a leader for the first round. And the important thing is that we elect this leader only in round 4, so the adversary can't know it in advance and can't use it in order to decide which round 4 messages will have a path to it and which will not. Okay, step 3, ordering the messages. The idea is to order each leader's entire causal history, and we want to do this locally by just looking at the DAG. This is also about 30 lines of pseudocode. So every node looks at its copy of the DAG and the selected leaders of the DAG. Now we know that processes may see the different views of the DAG with different subsets of it at different times. So it might be that the selected leader, some processes see it and others don't see it. So in order to be on the safe side, we commit mean use to order messages only leaders that have sufficient support in the DAG. Okay, then we know that they appear in sufficiently many DAGs. What do I mean? Well, this is basically the commit rule. The commit rule is this: if we have this leader in the first round, if we have two F+1 vertices in the fourth round that have paths to it, you can see that in this case, the condition is satisfied because we have these three yellow nodes have these yellow paths to the selected leader, then the leader is committed. Why is this okay to commit this leader? Because we know that every vertex in the next wave is going to have a strong path to this leader. Because every vertex in the next wave is going to point to n-f nodes from the round 4 of this wave, and it's going to see at least one with a strong path to this leader. Okay, so we know that once we got this much support, we know it's not going to go away. All the future leaders, future nodes, in particular the leaders, will have paths to this selected node. And now we say, okay, fine, then we can commit it. We do not reach consensus on whether to commit it or not. Okay, we just ensure that if one node commits it, all the others will have paths to it from the next leader. And this is what we need. Okay, some nodes might commit it because the commit rule will hold. Some others, the commit rule will not hold, but they will see it. And now we leverage a principle that is called in the literature the common core principle. And it appears in all kinds of textbooks. I don't know who deserves credit for pointing it out first, but it says that if you have 3 rounds of all-to-all sending and collecting accumulated sets of values from n-f processes, I know this is a mouthful, Poker processes will have at least 2f+1 common values. So what? Well, so that means that at least 2f+1 round 1 vertices satisfy the commit rule. This is exactly the commit rule. Okay, look at round 4 and see, are there 2f+1 values that refer to it? So because of this, we know that the elected vertex satisfies the commit rule probability at least 2/3. And it's unpredictable because we determine this leader only in round 4, and by then we already know if it satisfies the commit rule or not. And that gives us the order 1 expected latency until some leader is committed. Okay, because we have a constant probability of selecting a leader that is committed. What about the uncommitted leaders? Well, we have this leader in the first round here, and now we have a committed leader. This committed leader needs to check whether it should take into account the uncommitted leader or not. As I pointed out before, we know that by the commit rule, there's a path, a strong path from every committed leader to all previous leaders. So all we do is we go back along this path and we see if there are any leaders that we didn't commit in the past and that are on this path. And if they are, we commit them in order. Okay, this is going to ensure that all the nodes commit exactly the same leaders and exactly in the same order. And once we do that, each leader, we can sequence its messages by just looking at all of its causal history. And here we take into account the weak edges. We didn't take them into account so far, but in the committing and the election, but we take them into account now in order to ensure fairness. So that's it. That's the protocol. And it, as I mentioned before, it could be instantiated with different consensus algorithms, gossip-based, Reischuk, Verifiable, dispersal. And in these different settings, we get different communication costs, amortized communication costs, and different latencies. But the bottom line is that we can get lower latency than previous works. We ensure fairness, unlike previous works, and we have post-quantum safety, which is unlike previous works. So some nice new benefits to this new algorithm. And I guess the summary is that yes, it will scale. Okay. Questions?
Is there questions?
I have a question.
You have the elude, you can talk.
So I didn't get the weak edges and the delay question. So if a node process which is not faulty but very late issues its message very late, then how much does it delay finality or inclusion or what?
Right. So the I suppose, I don't know, you mean the finality of that process's messages or of other messages. So
when will this message be included, in which round?
This message will be included once. So there's a message, the message is very slow, right? Everybody's now in round 1000, and now I get a message from round 1, okay?
Yes.
This message doesn't have any strong edges because nobody received it on time to create strong edges to it.
Right.
But the minute I get it, my next message will include a weak edge to it. So once there is any leader that has a weak edge to this node, this message will be included. So the answer is it will get included as soon as it arrives at the node, at the process whose vertex is selected as a leader.
So basically, some future leader who sees this very late message will give it a favor and include it in its.
Yeah. Because we just make sure that all the messages are, all the causal history, all the messages that you received before have pointers. So there's never a message you received and you would not get it to be voted for.
Okay.
There is other questions. I have a very simple question. So in this algorithm, the last one, you assume that the Byzantine process are at most a third of the DAG, size. So, okay. And so another question, what will be the next challenge in this topic?
Will be the next work on this topic?
The next challenge for the community, which?
The next challenge?
Yes.
Oh, that's a very hard question. I think there are some things that are not solved. This protocol is very efficient for many messages, but it's very expensive for a single message because it sends, basically you need the linear number of transactions for it to pay off. So maybe something that doesn't have this might be interesting. Maybe something that uses weaker cryptographic tools or assumptions might be interesting as well.
Oh, okay.
Also, just finding an efficient way to actually do the communication and disseminate the messages and build the DAG, because we can assume this is an abstraction. I think these are kind of small things, not major challenges, but there are some things that are not resolved yet, and some things, how strong the adversary can be, I don't know if it's resolved yet, so we have this delayed adaptive adversary. How much weaker can the adversary be? How much trusted setup do you need in order to get, because we assume a public key infrastructure, some works assume more trusted setup and then, get better results out of it. So how much trusted setup do you need and how much you do with less? I guess, key distribution.
And I have also a question about the size of the message. It seems that you have no limitation on the size of what you can, what is sent at each one.
Well, it's a parameter that is decided by the algorithm, and the the reason I say it's a parameter is because it depends on which of these we use. So if we would use the gossip or bracha broadcast, we would send a linear number of messages. So once we get like n transactions and n minus f strong edges will broadcast the message. And with the verifiable the dispersal, actually for this to work out, to get an amortized cost of order n, we need to send in log n messages. So it's kind of a technicality, but the protocol is designed to accumulate the number of messages, whether be it n or n log n, and then to send them together.
Yes. Is there any questions?
I think maybe I want to, I kind of moved in because of the music. So I want to thank my co-authors again, Oded Naor, my PhD student who is here, and Lefteris and Sasha were probably still asleep because they're in California. So.
Okay. So we can say thank you to Idit Keidar.
Okay, thank you very much.